Deep learning, a subfield of machine learning, has emerged as a transformative force in artificial intelligence. Inspired by the structure and function of the human brain, deep learning models, known as artificial neural networks, are capable of learning intricate patterns from vast amounts of data, achieving remarkable performance in tasks ranging from image recognition to natural language processing. This article delves into the mechanics of deep learning, exploring its architecture, training process, and the factors influencing its complexity. At the heart of deep learning lies the artificial neural network. These networks are composed of interconnected layers of nodes or neurons, each playing a crucial role in information processing. The network typically consists of three types of layers: an input layer, one or more hidden layers, and an output layer. The input layer receives the raw data, such as pixels in an image or words in a sentence. The hidden layers, the true workhorses of deep learning, are where the model learns complex representations of the input data. Finally, the output layer produces the desired result, whether it's a classification, prediction, or generation. The magic of deep learning lies in its ability to learn hierarchical features. As data flows through the network, each layer extracts increasingly abstract and complex features. For instance, in image recognition, the first layers might detect edges and corners, while subsequent layers combine these features to recognize shapes, objects, and eventually entire scenes. This hierarchical learning allows deep learning models to automatically discover the most relevant features for a given task, eliminating the need for manual feature engineering, a process that was previously a bottleneck in traditional machine learning. The training of a deep learning model is an iterative process involving two key phases: forward propagation and back propagation. During forward propagation, data is fed into the input layer and passed through the network layer by layer until it reaches the output layer. The network's output is then compared to the actual target value, and the difference between the two, known as the error, is calculated. This error signal is then propagated back through the network during back propagation. During back propagation, the network adjusts the weights of the connections between neurons to minimize the error. This process is repeated many times, with the network gradually refining its weights and improving its accuracy. The complexity of a deep learning model, reflected in the number of layers and nodes, is a crucial design consideration. While there's no one-size-fits-all answer, several factors influence this choice. More complex tasks often necessitate deeper networks with more layers and nodes to capture the intricate relationships within the data. The availability of large data sets also supports the training of more complex models, as these models require substantial data to learn effectively. Furthermore, the computational resources available play a significant role. Training very large networks can be computationally intensive, requiring powerful hardware and significant time. Deep learning has revolutionized numerous fields, powering applications such as image recognition, natural language processing, speech recognition, and many more. Its ability to automatically learn complex features from vast amounts of data has enabled breakthroughs in areas previously considered intractable. As deep learning research continues to advance, we can expect to see even more innovative applications emerge, further solidifying its position as a cornerstone of modern artificial intelligence.